Welcome. I guess thank you for having me here. It's great that people are kind of making up all of this virtual hangouts, I guess, for people to kind of come together and still share science. Like Sayali said, my name is Sergio Cantu. I'm part of the Blockade group, and I'm here to, tell you a little bit about what we do in our research. Um, So I'm part of the Rydberg Polaritons team of the Blood and Blood group. We collaborate very closely with Michael Lukin, and so far the team that made most of the work that I'm going to be describing is basically Professor Vlad Vuletic, Professor Michael Lukin, and some other people. And I'm just going to here adding a picture of our overall group just to have a quick reference. But the Rydberg Polaritons team, what we really do is study quantum nonlinear optics. And nonlinear optics takes many shapes and platforms, but it can be really summarized as that they have one common goal, and that is that there needs to be strong interactions between individual photons, and with the hope that we can get a medium which radically gets different optical properties depending on either the frequency of the photons or the photon number that you put into this medium. A quick example of something like this would be, and yeah, just to emphasize that it is really this strong interactions between individual photons that we're focusing on. And an example of this would be, for example, a single photon switch. If one photon can negate the transmission of another, that would be great. And the other option would be if maybe the presence of a second control photon can impart a conditional phase onto a photon traveling, then the combination of these things, we could get a combination of different computational gates. And that has been kind of like the motivation behind our research. However, making nonlinearities is hard. As an example, if I take a two-level system, right? This system is extremely nonlinear if I just consider the single atom and the single photon, because the photon basically depends, the frequency of the photon leads to different scattering. But as far as the atom is concerned, because of saturation, then also the photon, once it's absorbed into the medium, no other photon can get absorbed. So that's already two different regimes, one in which the frequency of the photon matters as to what is the overall absorption into this atom, and the fact that once one photon gets absorbed, no other one can occupy that same atom, right? But if I look at the limitations of this problem, then if I take the cross section of the atom that the photon can scatter off, and I take the size of the beam, what is the diffraction limit of that this photon envelope can have, then you will see that the ratio between these two things means that the probability that a single photon is absorbed by a single atom is quite low. I think the best experimental numbers I have seen is something like 10%. Right? And you might say, well, but that's only for a single atom. Why not you just add more atoms and then the probability that you absorb increases? Well, that would be great, but unfortunately, the nonlinearity of your system will decrease with the number of atoms, right? Because if I have two atoms, then if I have two photons now, each one can absorb into one of the atoms independently. So I wouldn't notice whether the medium is saturated with photons or not. So for us, would be great if we can make something that basically once you have more atoms, it increases the likelihood that I can interact with the system, but without losing the nonlinearity. I want to be able to know that the whole system has one photon, two photons, three photons in the medium. So for this, I'm going to basically give a quick outline of my talk. One is I'm going to give you the quick recipe as to how we do these interactions between photons. And then I'm going to go into a couple of examples that we engineer interactions between photons. I'm going to go into attractive interactions, repulsive interactions. And then from these repulsive interactions, I'm going to go into some emergent phenomena that I think that is quite interesting. So maybe we can start with the quick recipe for photon-photon interactions. So for photon-photon interactions, what we do is that we need to figure out a way for the photons to, as photons travel, they don't have mass, they don't have charge. So we would like to modify the photons such that when they travel, they sense each other, right? So because we would like photons to behave almost like atoms. Well, maybe we can figure out a way to strongly coherently couple photons to the atoms and then make the atoms interact and then see what happens. So yeah, so the recipe goes as follows. So we need to find a strong coherent coupling between photons and atoms, or another way to think about it is make photons behave like atoms. And then if we can figure out a way for atoms to interact very strongly, it will give photons an interaction potential. And then that would make photons interact with each other. So that would make basically photons interact as massive particles. So to do the first part of the recipe, we need to figure out how to coherently couple photons into an atomic ensemble. And for that, we're going to take a quick example of this. So if you take a two-level system, you get your typical absorption profile exactly at the resonance of the atomic resonance. And then once we add a third level and we start coupling strongly to that, then if once we reach the two-photon resonance between this three-level system, then the system opens a transparency due to the construction destructive interference between the different states that are available. And what that leads to is basically electromagnetically induced transparency. And the way it looks is basically like this. So you have your two-level system, which is normally absorptive, but when your laser is exactly on resonance with that three-level system now, then that leads to a completely transparency. So now the medium that before was absorptive has become entirely transparent, and the photon propagates through no problem. But if we look at what is the state of the photon as it propagates through, we would find that in that peak that you see, the photon is traveling in this linear superposition between ground and excited states. And that is interesting because now that means that as the photon propagates, even though it, at the end of the day, it transmits entirely, it has no recollection that there were even atoms in there. As it propagated through, it traveled as to this linear superposition between photon and atom. And this atomic excitation now we can use to make photons interact with one another. So maybe we can go further. So now that we have figured out that photons, as they travel through this cloud, they propagate as this linear superposition between photon and Rydberg atom, then we can see how strong can these atoms really interact. So and just to kind of drive that point home, in our case, the density of atoms is very large. And what that means is that this linear superposition state is mostly an atomic excitation. It's basically what you can think of it as the photon propagates through, the mapping to this state makes it almost entirely this atomic excitation. So it's almost like a, kind of like a wave in a stadium during a soccer match. So yeah. So the type of atoms that we couple to, the type of atomic state that we couple to, just to give you some comparison. So Rydberg atoms are, atoms that are quite large. So if you compare them to the ground states, the dipole moments that they can get are almost at the micrometer level, and that makes them quite large. And the reason for this is that that the electron keeps just getting looser and looser bound to the nucleus, and that makes the electron, the orbital of the electron further and further out. But as a consequence of this, since the electron is so far removed from the nucleus, the coupling to the ground state gets also weaker. So that means that you can have, in theory, Rydberg atoms can have up to millisecond lifetimes if you manage to excite them. So that's already kind of twofold advantage. One is that if you manage to make a Rydberg atom, it's almost microscopic. And the other advantage is that the coupling to the ground state is quite low, so you get very low decay rate down to the ground state. But the other reason that this the fact that this dipole moment is so large, then that means that if I have two Rydberg atoms and they're kind of of different parity, then they can interact quite strongly. So this dipole interactions goes n to the fourth, and you can also have van der Waals interactions, which go to n to the 11, and that is when you have two Rydberg atoms of the same atomic state, or atoms with the same parity. They don't have to be necessarily the same quantum number, but the pair needs to be the same. And for us, this interaction can be quite strong. We usually work at n equals 100, and for us, it means that the C6 interaction coefficient for us is 1.8 terahertz per micrometer to the 6. So this interaction basically dies off rather quickly, but as far as the photon is concerned, you will find that you don't have to be basically the two Rydberg atoms on top of each other to feel this strong interaction. So now we have basically two parts of a recipe. One is that photons can map coherently to atomic states, and the second one is that atoms for very large quantum number can interact quite strongly. So what does that mean for us to kind of put that all together? So a quick example for that is if I take two atoms, each of them in the ground state, and they're separated, very, very large, then if I try to, if I kind of keep track of the manifold of the bases that I'm in which I keep track of how many excitations I have, then I would get basically the following levels, right? I would get the ground atomic state. I will get the manifold that corresponds to either one of these atoms excited, which is a GR or G state, and the two of them excited, right? So coupling from the ground state to that first manifold is no problem because I only have one excitation. So there's no interaction energy that prevents me from coupling them. But for the second one, the distance is what really matters. If the atoms are very far apart, then I should be able to couple this two atoms up to the Rydberg state, no problem. But if these atoms are very close, because of these dipole interactions, the van der Waals interactions, then you will find that only one of them can be excited, and the second one, the atomic state will be basically now completely repelled due to the interactions. So that means that I can only at most have one excitation. So this is quite interesting because now if I have n atoms and the density of atoms is such that they are all within this interaction region, then I have the likelihood that which I can absorb into one of these atoms goes as basically n, but the nonlinearity is still there. I can now I am basically aware whether I have one photon or 0 photons in there. So which is kind of nice. And then so just to drive the point home, how much I can couple to that second state depends on the excitation line width of the transparency that we found above. So that means that for us, effectively, the distance of atoms that the distance of the photons can be before they start kind of blocking each other is in the order of 10 micrometers. This is much larger than the size of the Rydberg atom, because in here what is important is how close can the atoms be before the electric fields due to the dipole move them out of the two-photon resonance. So that's a much more sensitive distance. So that's why it's actually much larger than just the atom dipole size. So what does this mean for the photons? It means that if I have a cloud of atoms and I have a one photon in the middle, right, then I can split this cloud into two regions, right? The region that is within this interaction volume for the photons and the region that is outside this interaction region. In the region that is outside, it's basically as if there's no other photon in the medium. The photons will travel completely transparent, completely no problem. They will just go through. But in the region in between is when things get interesting, because now that extra Rydberg level is not there, it breaks the transparency. And now I'm again sensitive to where this two-level system is, right? What is the frequency of the photons that I have? For example, if this photon is on resonance with the two-level system, then I would get absorption. If it's off resonance, then you can have other behaviors. And really in this case, what matters is the number of atoms that are within this blockaded volume. And this is where the interaction, basically now we can start engineering interactions between photons, because This is really you can think of it as a distance dependent spectrum, right? It depends on how far apart these two photons are from one another. So in our experiment, what we're doing is just to ensure that photons cannot circumvent one another. We just focus the photons so tight as close to the diffraction limit as possible, such that because of the interaction volume, that the photons cannot go around each other. So they're if they interact, they are forced to travel in one dimension as we could make. So. And we're also working at very high densities, such that once these photons are interacting, there's enough atoms underneath the interaction region such that they can sense each other. So, okay, so I think that now we have both components of how we make this photons interact. So now let's go into, well, now that they are kind of sensitive to each other, then we can start talking about, well, what type of interactions can we engineer? What we would like these photons to do. So from there, I'm going to go into now the region of attractive interactions. So again, going back to this electromagnetically induced transparency, if we work off two-level resonance, then you will find that the state is still the same. You get this dark state. But if I look at the spectrum of the photons coming out, you would find that you have that peak that corresponds to the electromagnetically induced transparency. And there's an extra consequence of this, that because of this two-photon resonance, the phase that the photons acquire as they propagate through the cloud is basically negligible, is zero. When we say that this is electromagnetically induced transparency, it really means transparency. The photons have no memory that the atoms were there. They just kind of propagate it through. But that is only for the, so as the photons are propagating through, you will find that the group velocity is suppressed. And that is because as they propagate through, they're not in a photon-only state. This linear superposition makes it so that the group velocity of the photons traveling is greatly suppressed. So in our case, we can reduce the group velocity of the photons up to 100 meters per second. So that is something that will be interesting later, because now any interaction that we make in the medium, the slower these photons travel, then the more time they have to basically interact, right? So that any correlations that we can make, we can enhance the features that we see by having the photons travel slower and slower. So, but just to kind of now drive this point home, if now we compare with what the two-level system looks like, right, in this region where the Rydberg atoms interact in such that now they're completely blockaded. So then that means that, so if I look at the transmission point looks exactly the same. So where you see that crossing point between the green and the blue. But if you look at the phase, you would find that although for electromagnetically induced transparency, there's no phase, there's some phase that is acquired for the photons as they propagate in this two-level system. So now I would like to focus on this difference in phase, right? So the transmission of the photons, I don't know, as the photons come out, the transmission doesn't depend on whether there's one photon or two photons around it. They just kind of come out and the transmission is exactly the same. But the phase is quite different. If the photons were separated very far apart, then they will have no phase. But if the photons kind of came in together, they would have this negative phase corresponding to this green trace. So if I make a trace of this, right, so just kind of to drive this home, if I cannot plot the phase as a function of separation, then you would see that, well, I think there's a minus sign here, but you would find that for very close separation, you will get some saturated regime in which the Rydberg atom just completely blockaded your atoms. But as they kind of get separated more and more, then you get this, you get the phase kind of goes back to zero. And that means that you're kind of going back to your transparent medium. But now what you have is basically this distance-dependent phase. You can think of it as nothing else but an interaction potential. it actually even looks like a step well. And in the parameters that I have plotted, you would find that the effective mass as the photons propagating through, the kinetic energy of the photons as they travel through, you will find that it's actually negative. And what that means is that once I put this whole thing into, once I take the whole 2-photon state with the Hamiltonian that corresponds to the parameters shown, you would find that you can actually, collapse all of the interactions, all of the parameters into a very simple Schrodinger-like equation. And all that matters here is the interaction potential that the photons feel, which corresponds to this phase, and the kinetic energy that they acquire due to the fact that they're not entirely photons. There's this combination of photon and atomic excitation. So you can put all of this together, and you would find that it quite nicely looks like this Schrodinger-like equation. And then what that means is that, well, now we can really engineer through the phase that the photons acquire as they propagate through, far apart versus close. And now that the fact that they are traveling through with a particular group velocity, now we have all the pieces that we can have basically attractive interactions. So for us in this particular Schrodinger equation, we kind of tune the parameters such that we get an attractive potential, almost like a bucket-like potential effectively. And what we see in that case is that the photons coming out, if I look at the probability of detecting 2 photons, the likelihood that they're coming out together is much larger than further apart. And that is because the interaction potential that we have engineered makes it such that they prefer to be close together than far apart. I would like to now maybe drive this point home that it is really this phase between the 2-level versus the 3-level system and how the overall potential looks like as a function of distance that allows us to control what the photons are doing as they propagate through. But the limitation in the 3-level system means that, as we kind of change the relative, as we try to engineer the interactions that we get, we found that we were kind of stuck. We were not able to make other than attractive interactions. And that is because even though we can make the potential flip sign and give us, a step or a bucket-like potential, we found that the effective kinetic energy of the photons traveling was always such that once you flip the sign of the potential, the sign of the kinetic energy flips as well. What this means is that you always end up with an attractive interaction between these photons. So we decided, okay, how can we make an interaction potential that doesn't flip the sign of the mass, or maybe we can keep one fixed while we switch the sign of the other, with the hope that we can get repulsive interactions, right? And that is basically the next part of my talk. So what we decided to do is basically add another EIT to the system. And this is because now with this 2 EIT system, you can really control and tune the overall dispersion of the photons traveling through. You can control what the effective phase between the inside the interacting region is versus outside. And this level of control has allowed us to, for one, replicate the type of interactions that we saw before. So we were able to get these attractive interactions by having kind of photons bunch as they come out. And we were able to create also basically a coherent state, or a state that has anti-bunching for very low times, which means that the probability that detecting 2 photons is quite low. But we see that the probability of detecting 2 photons actually is enhanced relative to the the single photons by quite a lot, and then it kind of dies off at a distance. So the way that we think of this is that the photons are just coherently pushing each other, and then kind of they you can think of it as the distance that they prefer to be at is this kind of 100 nanoseconds time difference. And that is because as they travel through, they kind of push each other out, and we see the correlations arise. But this is only for 2 photons. Something that we were kind of curious about is, well, what happens when you have 3 photons in, right? Like if I have 3 photons and they're repelling, you can think a very quick picture is, well, if I have 2 on the sides and 1 in the middle, then if they're really repelling, there must be a distance in which they kind of almost make a quick lattice, right? Like something like a lattice, because they're equally repelling. So you might have kind of like a squeeze state in the middle. So that's basically what we started to look. So we started detecting 3 photons and comparing that to what is the likelihood of detecting each pair, right? Just to normalize things properly. And what we saw is that, for 0 times of arrival, right, the likelihood that I detect 2 photons means that the third one, given that I detect 2 photons, what is the likelihood that I find the third one? That's the plot that I'm showing here, where, I'm kind of separating the 2 photons that I detect over each one of these panels. And then, so if the 2 photons are on top of each other, then the likelihood that I find the third one means that it is quite repelled. You can see that, the likelihood that I find the third one in the center is quite reduced. But as I start separating these 2 photons, I will find a region in between that you can see that there's almost that peak that arises, right? And then it gets to 100 nanoseconds, and that's what gives me the highest peak in the middle. And that is when the third photon is basically stuck in between the other 2. And then if I separate these 2 photons further out, then I just recover the previous slide of the 2 photons interacting repulsively, where this kind of 2 photons that are very largely separated don't know of each other, right? They're so far apart removed that I can think of it as each independent repulsive photon. So now if I plot the point in the middle, right, as a function of that, the 2 photons kind of separated, you would find that this, we see this kind of hint of something building up, right? You can get this quite high state that corresponds to, the 2 photons on the side, just kind of squeezing in the third one in. And then as they kind of get more and more separated, then any correlations kind of just die off. And this, I think, to me, is quite interesting, because now you have photons that are traveling through this medium that makes them interact repulsively, and they start to almost self-order, right? If I start adding more photons into the system, then I would expect that, maybe I would get something like an accordion, right? Like, very tightly packed in the middle and then kind of loosely packed on the outside, on the edges. So for us, something that you could think about is maybe if we can start engineering longer chains of photons, maybe we could get more and more correlated states of light. So, and something that I think for us is also quite interesting is something that I didn't spend a lot of time on is, well, as the photon propagates, it becomes this, saturated medium, right? Only one excitation can live there. But that state is also interesting in and on itself, because you can think of it as now you have the superatom state in which you have a coherent superposition of maybe the photon was absorbed by, atom I, and then you have basically the combination of all the different atoms within that volume. But now you have this kind of W state, right, that you can now use to drive coherent oscillations between the ground state and this particular state. And this state will be much faster to couple to the more atoms you have. And this is something that is known as a Rydberg superatom. And for us, it would be interesting to see, well, as now that we have been kind of studying the photonic part of things, if we can now flip the script and now think about, well, is there anything in the correlations of the atoms that we can learn more of as we go forward now, trying to manipulate, the atoms and maybe engineer different shapes of clouds? Maybe we can figure out a way for atoms to also interact across different ensembles. That's just kind of something that we're thinking about a lot lately. And with that, I think, yeah, so this is just kind of thinking of this Rydberg superatom. And I think for me, it's pretty much it. I think, it's just how we can kind of think of these attractive interactions, how we're able to kind of get them into this repulsive regime. And now we're thinking a little bit more as to how we can use the Rydberg superatoms as coherent atom states to lead to some interesting interactions.
Well, thank you very much, Sergio.
Thank you.
I'm going to meet everyone. Thank you for a very nice talk. So if anyone have questions, please write it in the chat or just unmute and do the questions.
So I just wanted to tell something before. Someone had a question on the YouTube chat. I don't know if he saw the answer, but I tried to answer to him using the YouTube chat so that this person can know. I did.
Perhaps I have a question.
Yeah.
Hi, Sergio. Thank you for your talk.
Thank you.
I was very interested in the last part you presented, this sort of emergence of a sort of photonic crystal type behavior.
Yeah.
But for me, this sort of invokes an equilibrium type of feeling, right? Like the formation of a crystalline state. But this system is very far from equilibrium, I assume, right? So how do you think about this?
Yeah, I guess, you could think of, I guess the way I think of it is that if we can saturate the medium with photons, right? So you're saying, well, you're kind of conditioning on detecting photons, so it's not really equilibrated, right? You're just kind of saying, okay, I detected 2, and then I see what the third one is. In our case, I guess, it's always moving, right? So that would be, but the state itself, I think that if we can quench into it by having a lot of photons, I believe that for a long enough, dense enough medium, we should be able to completely map any photon state that you put in. As long as you put enough photons, they should be able to organize into this crystalline state. I think the problem here is that, for our system, our system is neither long enough or dense enough for the photons to completely collapse into that state. I think that, yeah.
But so then, is it possible, or have you defined something like a thermal equilibrium or a thermalization time? Do you know how long your medium would have to be to see these effects?
I think so. It would have to be quite long, because I think the problem is that, the second part is that the edges are not attractively, interacting with the rest of the chain, right? So that means that the lattice spacing between the train would be, in the middle would be very tight. It would be, very well defined, but on the outside is the problem. At the edges is where you would have some trouble. So I guess you would have to have I think for us, we would have to have, I think that the density is fine, but the length is really the problem. So, but I think, for those lengths, I don't know if it's feasible to get. So I think that you would get something like maybe 200 micrometer long cloud with an ODB of 5, I would say, or deeper blockade radius of 5, I think would give you already something that is quite quenched. But I think that the problem there would be, what is happening at the edges to really call it a lattice. I think that's the biggest limitation. Yeah.
Okay, thank you.
Mm-hmm.
Good. So anyone else have any questions?
So, in the superatom part, have you done Rabi have you observed Rabi oscillation in this superatom part, or have you done experiments in that part?
So this is something that we're thinking about. We haven't implemented it. We're kind of working on making some progress to get to that regime in which we can get, this kind of atom arrays. I think that in that case will be interesting. So something that, so in that case, the coupling to the Rydberg state is quite fast. But when you go into, if I have now 2 ensembles and I look at the interactions between them, because there's still only one excitation between them, there's not a lot of enhancement over the interactions. But I think that it will be something interesting to see how the coherence between these ensembles moves, right? Because now you have this kind of 2 W states, and to have them interact, I think it will be interesting to see whether this coherent states, how the coherence moves around, whether there's some phase interference that leads you to maybe a rotated W state, or, something that allows you to see interesting features arising. So,
and And how many number of atoms you think you might have in the superatom?
We're thinking of maybe something close to 100 to 1,000 atoms per trap.
So it's a dipole trap.
Yeah, it would be in the atomic tweezer. Yeah.
Okay. Mm-hmm.
Mhm.
Thank you.
So I actually have a question.
Yeah.
So regarding this measurement of the photons, when you say that you sometimes have one and sometimes two photons, you do a kind of homodyne detection, or how you measure these photons?
Yes, so we do a what is essentially a homodyne measurement. So what we do is basically we have two photon detectors, with a 50-50 beam splitter, and then we just look at the times of arrival of each photon, and then we basically cross correlate both detectors, and we compare that relative to the average photon rate in each one. So it's basically comparing what is the average two photon state, or what is the average number of two photons that we get versus the square of the average of single photons. So that's what basically the what we're measuring there. So it's all our measurements are relative to the how they differ from the usual Poisson distribution, I would say.
And you talk that these are bound states, but I wonder if they are actually, these photons are entangled.
You worry that they are, so I would say they are heavily correlated, right? Because as they come out, then I don't know if entangle, so detecting one doesn't ensure that there will be a second one on top. So I don't know if it is quite as close
If it's
to
right to say that it's entanglement.
Yeah, I would call it more strongly correlated, because it is really more likely that I would have a second one in, but it's not a heralded type measurement. Yeah.
Exactly. Okay. Thanks.
Just one more question. So have people done this coherent W state interaction between superatoms already? I think.
So Mark Safman's group, I think, is one that comes to mind, that they have seen this coherent oscillation across. They basically have quite a lot of atoms, and they see a coherent oscillation that depends on the number of atoms in the ensemble.
Yeah.
I think they tried seeing interactions across ensembles, but I don't remember whether they were able to see any sort of interaction, basically other than regular interactions, I would say.
But I think they have not done it more than 15 atoms.
So the oscillations, they were able to see something like, I think they had one experiment where they got 100. That's the one that has but the problem is that it dies off rather quickly. So the atoms dephase quite fast. I think that has been the biggest limitation, in that the number of oscillations that you can get before things dephase is quite rapid. And then in that case, I don't know whether the problem is, so with Rydberg superatoms, you can have two problems. One is that as they dephase, you can ask, well, is it dephasing because is the state rotating into something that maybe becomes dark to my driving field? And the other question is it dephasing because I'm losing atoms in my W state, right? Am I mapping from some W state of n atoms to a W state of n minus 1 atoms, and so forth? So those, I would say, I don't think that those are questions that have been asked. So answered. But yeah, something of interest would be if we can maintain the coherence and then see how the interactions move the coherence around.
Okay. Thanks. You're mute, Manuel.
So I think there is no further questions. I think YouTube also, there is no more questions. So with that, I think we can thanks again our today's speakers, to Sergio and Dennis. And And well, thanks to everyone who come today to hear this talk. We are having some technical issues, but we expect to improve and fine tune with the time. And stay tuned to our website, to our Twitter, Facebook, social medias, and then we will be announcing the next speakers for the coming weeks. So again, thank you very much, and see you soon. Have a good day.
Thank
Bye.
you.